In this video, I want us to take a look at some past questions on redox reaction. And these questions are from WASSCE, WASSCE past questions. So this is to get you ready for your examination. All right. Now, you will see questions like this, which will say define oxidation and reduction in terms of, and they say the first one is transfer of electrons. Okay. Transfer of electrons. And the second one is change in oxidation number. So if you read over your notes, you have reduction. So under reduction, you know that transfer of electron is about gaining electron when we are talking about reduction. So reduction refers to the gaining of electron. Gaining of electrons. And then what about change in oxidation number? Now when it comes to change in oxidation number, the oxidation number is going to decrease. Decrease in oxidation number. Okay. What about oxidation? For oxidation, now for oxidation, when it comes to transfer of electrons, we are losing electrons. So loss of electrons, that is oxidation. What about oxidation number? There's going to be an increase in oxidation number. There's going to be an increase in oxidation number. So this is how you answer this particular question. But also remember that when it comes to reduction, it is sometimes also defined as addition of hydrogen. Addition of hydrogen, and oxidation is removal of hydrogen. Okay, so this is some of the ways that oxidation and reduction can be defined. Okay, now you also find questions where you are asked to calculate the oxidation number. So for example, you will be asked to identify the oxidation number of manganese in MnO4 minus. So you have manganese where you have to identify its oxidation number, right? Oxidation number. Or you can be given a species like H2SO4, where you've been asked to identify the oxidation number of sulfur. Now, before you do that, there are some quick things for you to remember. Always remember that hydrogen, or let's start with oxygen. Oxygen is going to have an oxidation state of -2. Oxygen is having an oxidation state of -2 in most of its compounds. Okay, and when you have some compounds like peroxides, oxygen will have an oxidation state of -1 in peroxide. So for example, if you have hydrogen peroxide H2O2, oxidation state of oxygen will be -1. So in short, they represent oxygen with O2 2 minus. Okay. Now, when you have superoxides, for superoxide, oxidation state of oxygen is -1/2. So, for example, if we have something like potassium dioxide, K2O, oxidation state of oxygen here is -1/2. So, it is represented by O2, O2 minus 1. Okay. All right. So, well, this is how to go about oxidation states when you have oxygen in there. And what about hydrogen? For hydrogen, generally it has an oxidation state of plus 1. It has an oxidation state of plus 1 in most of its compound, in exception of hydrides of some metals like group 1 metals. So, and if you have hydrides, in hydrides of group 1, hydrogen will be having an oxidation state of minus 1. So those metals, hydrides of group 1 or group 2, so hydrogen will have an oxidation state of minus 1. So these are some of the exceptions that you have to take note of. But mostly you have something friendly. So for example, in this particular example, you have MnO4 and you have H2SO4. Okay, so how do you find the oxidation state of manganese? So let's call the oxidation state of manganese X, and then we are adding everything, and then we'll equate it to whatever value we have here. All right. So if the oxidation state of manganese is X, then we'll multiply it by the number of oxygens we have times the oxidation state of oxygen. So oxygen there is minus 2, and so equals minus 1. So x minus 8 equals minus 1. So x will be equal to minus 1 plus 8. So x will be equal to plus 7. So the oxidation state of manganese over here is plus 7. Okay. Now, what about H2SO4? For H2SO4, hydrogen, we're interested in the oxidation state of sulfur. Hydrogen is always plus 1 in most cases. So over here too, it is plus 1. So we'll have two hydrogens each with plus 1. Okay. And then we have the sulfur, which we don't know. So let's call it X. And then we have four oxygens each with minus 2 equals 0. There is no charge here, so it's equal to 0. So this is 2 plus x minus 8 equals 0. So x is going to be equal to, if we take minus 8, it becomes plus 8. If we take plus 2 to the other side, it becomes minus 2. So x will be equal to plus 6. So that's how you calculate oxidation number. And you also have to know how to balance your oxidation equation or redox equation. And if you don't know that yet, then check the description of this video. You'll find the link to how to balance redox equations. All right. Now let's look at the next question. Now this question says, in a reaction, it was found that 3.0 grams of a metal X was oxidized by 25 cm cube of 0.10 mole per dm cube K2Cr2O7 under acidic conditions. Okay, now the question says that deduce the mole ratio between X and chromate anions. Then it says write a balanced equation for the redox reaction. Then it says give the oxidation number of chromium and X in both reduced and oxidized form. Okay, so let's look at how we can solve this question. All right, now let's take note of the things we have there. We are given the volume of potassium chromate. We are also given the concentration. So once you see volume and concentration, what comes to mind first? Mole. You'll be able to find the mole. Okay. And we are also given the mass of the metal. We are given the mass of the metal. So mass of X is given to us as 3.0 grams. And then we also know its molar mass to be equal to 200.6 grams per mole. Okay, what this means is that the we can find the mole of X because mole of X is going to be mass over molar mass. Okay, so mass over molar mass we have 3.0 grams over 200.6 grams per mole. And the grams, of course, will cancel out. And so we'll have, if you punch this in the calculator, we're going to have 0.015 moles of X. So that's the mole of X. Now, we also need to find the mole of chromate because we are trying to deduce the mole ratio between the two. Okay, so for volume of chromate or potassium chromate is given to us to be K2Cr2 7 is 25 cm cube, 25.0 cm cube, which is equivalent to 0.025 dm cube. Okay, sorry, dm cube. So remember to convert your volume to decimeter cube. And how do you do that? You divide through by 1000. And so that is what we did, and we have 0.025 dm cube for the volume of potassium chromate. All right. And now we are also given the concentration of K2Cr2O7 is given to us to be 0.1 mole per gm cube. Okay, that means that the mole of K2Cr2O7 can be calculated as concentration times volume. So we have concentration times volume, where the concentration is 0.10 times the volume, which is 0.025 dm cube. So what do we get for this? So when we put the calculator, we'll have the mole of chromate anions in the solution to be 0.0025 moles. Okay, so that's going to be the mole of the chromate anions. So the question says, what is the mole ratio between the two? Now, the mole ratio between the two can be expressed as mole of X over the mole of chromate Cr2O7 2 minus. So when the potassium is gone, we have chromate anions. Okay. So what is the mole ratio between the two? We'll find out when we divide the two. So for the mole of X, we found it to be 0.015, and that of chromate is 0.0025 moles. Okay. Now, when we divide through the two, this one can go into itself 1, and it will go into this 6 times. So this simply means that the mole ratio between the two is 6 is to 1. 6 is to 1. So how do we conclude? We conclude that mole ratio of X to the mole of chromate Cr2O72 minus is 6 is to 1. Okay, so that is how we work out the answer to this particular problem. Then the last part of the question says that keep the oxidation numbers of chromium. Anyways, the second question says write a balanced equation for the redox reaction. A balanced equation for the redox reaction. All right, so let's see how we can do that. So for a balanced equation for the two equation II, now we have chromate Cr2O72 minus. Now we're told that the chromate was used, okay, to oxidize the metal. Okay, what that means is that the potassium chromate is going to be reduced. So what is causing the other one to oxidize is going to be reduced itself. Okay. Now, chromate anion, this is a chromate anion. When we are writing redox, we are not going to include the metal. Okay, so we have chromate. Now, chromate, the central atom there is chromium. Its reduced form is going to be chromium 3 plus. So all we have to do is to balance this, and this is going to be our reduction half. So let's say reduction half. So for the reduction half, we will have to balance this Cr2O72 minus, which is giving us chromium 3 plus. Again, if you don't know how to balance redox equations, check the description on this video and follow the link to watch our video on balancing redox equations. Okay, now if you check the left side, you have two chromiums, and on the right side is only one. So we have to balance that. So we do that by bringing two here. Okay, so the chromium is balanced. Now, how do we balance oxygen? Remember, this is acidic medium. Okay, so to balance oxygen, we will have to count the number of oxygens we have there, which is 7. So if we have 7 oxygens, then what do? We balance it by introducing water. So we introduce 7 moles of water. Okay, so now we have 7 oxygens on the right, and then we have 7 oxygens on the left. But then there is one thing left, hydrogen. We have 14 hydrogens on the right, but we do not have any hydrogen on the left. So we balance hydrogen by bringing 14 H plus. Okay, so now every element there is balanced except one thing, the charge. So over here we have the charge here on chromium to be plus 3, and if you multiply it by 2, that's going to be plus 6. So on the right side, we have a total charge of plus 6, but on the left, we have 2 minus here, and then we have plus 1. This plus 1 times 14 will give us what? Plus 14. So plus 14 minus 2 will give us a total charge of plus 12. So all we have to do is to add electrons, is to add some electrons to the left side so that the charge on the left will become equal to the charge on the right. So let's add 6 electrons, Cr2O72 minus plus 14 H plus. Okay, now when we add 6 electrons, it will balance the charge. So we have 2 Cr3 plus 7H2O. 7H2O. So let's do the calculation again. 2 times 3 plus will give us 6 plus. And over here we have 14 plus. Okay, 14 plus. And then the electron we just added has a negative charge. So 6 times minus 1 give us minus 6. So minus 6 plus 14 is going to give us what? Plus 8. That plus 8 minus these two will give us plus 6. So the charge on both sides is now balanced. So the next thing we have to do is to balance x. Is to balance x. Now we have x, which has been oxidized, and so the oxidized form of x is going to be x plus. Okay, that means that it has lost an electron. But then we've been told that the mole ratio between chromate anion and then, or we work it out, that the mole ratio between chromate anion and x is 6, is 1 is to 6. Okay, so for 1 mole of chromate anion, we should have 6 of x. Okay, if we have 6 of x, then it has to run through. So 6 of x, and the electron will also have to be 6. Okay, so the final thing to do is to combine the two equations. When we combine the two equations, we can see that the electrons will cancel out. This will cancel this. So combining this, we'll have Cr2O72 minus and plus 6 6x plus 14h plus, okay. And on the right, we are going to have 2Cr3 plus 6x plus 6x plus and water, 7 moles of water. Okay, so that's going to be our balanced equation. All right. Then the last part of the question says that it says give the oxidation numbers of chromium and X in both reduced and oxidized form. All right, so now reduced form, in the reduced form, chromium has been reduced to chromium 3 plus, okay, chromium 3 plus. So we'll say that for chromium 3 plus, the oxidation number is going to be plus 3, okay, in the reduced form. All right. And then for the reduced form, X was oxidized. That means that before it has been oxidized, what is the oxidation state? It is a metal and it's going to be in its natural state. So the oxidation is going to be at 0. Okay. Now, the oxidized form, for the oxidized form, before chromium or chromate has been oxidized, has been reduced, what is its oxidation state? 072 minus. So if you work out the oxidation state of chromium from here, you'll find out that it is plus 6. Okay, it is plus 6. Now for X, it has been oxidized to plus 1, plus 1. So this is how you write the oxidation state of species. You write the charge and then you bring the number. Okay, all right. Now let's look at our last question. Our last question says that write a balanced equation for the following reactions. And we have been given this reaction. Okay, this is the reaction. Now we've been asked to write a balanced equation for the reaction. So let's see how we go about that. Now you can feel free to pause the video and try balancing the equation yourself and see if you get the right thing. All right. So first, oxidation half. Oxidation half. For the oxidation half, we said oxidation is loss of electrons. So if you observe from the equation, you can see that ion 2 plus has been oxidized to ion 3 plus. Okay, it has lost 1 electron. So this is going to be our oxidation half. So we have Fe2 plus being oxidized to Fe3 plus. That means that ion here has lost 1 electron. It has lost 1 electron. So it is balanced. It is balanced. All right. Now you have to go back there and observe again what has been reduced. Now over here, when you calculate the oxidation state of manganese, you will find out that it is plus 7. Okay. And over here, it is what? Plus 2. So that means that the the potassium permanganate, the manganese anion, has undergone reduction. Okay, so that is going to be a reduction half. For the reduction half, so for the reduction half, we have MnO4 minus 2 Mn2 plus. Mn2 plus. So again, we have to make sure that everything is balanced. Now the manganese here is 1 and over here it's 1. So it is balanced in terms of numbers. What about oxygen? Oxygen here is 4, but we do not have any oxygen here. So how do we balance oxygen? We introduce water, and the water will have the same number as the number of oxygen that we have on the side that has the oxygen. Okay, so over here we have 4 oxygen atoms, so we'll introduce 4 moles of water. So MnO4 minus, giving us Mn2 plus 4 moles of water, 4 moles of water. So oxygen is balanced. And then we have introduced something new, which is hydrogen. We have 8 hydrogen atoms here, 4 times 2, 8. And over here we have none. So we are balancing it by introducing 8 moles of H plus. Okay, so we've balanced hydrogen. We have balanced hydrogen. Okay, so the next thing to do is to balance the charge. To balance the charge, we know that on the right we have a charge of plus 2. That is a net charge there. Then on the left, we have 8 plus, 8 times plus 1 give us 8 plus. And then we have minus 1 here. So the net charge is plus 7. Okay. So we'll have to do something to this to make it plus 2, just like the right side. So we introduce electrons. So the overall balanced equation for the reduction half will be like this. MnO4 minus plus 8 plus 5 electrons to give us Mn2 plus 4 moles of water. Okay, so if you calculate the charge on the left, you realize we have 8 minus 1, which will give us plus 7 minus 5, which will give us plus 2, which is the same as what we have on the right side. So the reduction half is balanced. Now the only thing left is to combine the two. Remember, the oxidation half gives us Fe2 plus to Fe3 plus 1 electron. Okay, now we have to make the electrons the same so that we'll be able to cancel it out. So what we have to do is to multiply through by 5. So times 5 will give us 5. We do the same thing to Fe3 plus and the same thing to Fe2 plus. So this will cancel this. Okay, and our overall equation is going to be MnO4 minus plus 5 Fe2 plus, okay, plus 8H plus, and then on the right we are going to have 5 Fe3 plus Mn2 plus and 4 moles of water. So this is our balanced redox equation. So we are done with the first part. The second part of the question says that it says a sample of iron ore of mass, so II. It says that we have an iron ore, so we have mass of ore to be 0.350 grams, okay, was reduced to Fe2 plus in acidic medium. Then the solution was titrated against 1.621 times 10 exponent minus 2 mole per dm cube potassium permanganate. 41.50 cm cube of KMnO4 solution was required to complete the reaction. Determine the percentage by mass of ion in the ore. Okay, all right. So we have an iron ore of this mass 0.350, and from what the question is telling us that is that the ore has some impurities and it has some pure iron. So we are trying to find the percentage of pure iron in the ore. Okay, so how do we go about that? The trick is to try to find the mass of iron itself in the ore. Then we divide it by the total mass of the ore and multiply by 100. That will give us the percentage. So let's start by trying to find the mole of KMnO4 that's reacted with the ion. Okay, so we have the concentration of KMnO4 to be 1.621 times 10 exponent minus 2 mole per dm cube. Okay, then we also have the volume that's reacted that was gotten from the theta value. Okay, that is 40. So volume of KMnO4 is 41.50 cm cube, and this will be equal to 0.04150 dm cube. Okay, now so what is the mole of the manganate MnO4 minus, assuming we do not write the potassium, the mole of MnO4 minus in the solution? It is going to be the concentration times the volume. So the concentration is 1.621 times 10 exponent minus 2 times the volume. The volume is 0.04150. 0.04150. Okay, and what do we get? We are going to have a total of 0.727 times 10 exponents minus 4 mole. So that is a mole of MnO4 that's reacted. Okay, so if that is what happened, then we'll have to go back to our balanced equation, and then we use that to find the mole of Fe2 plus, because the Fe2 plus is what we had from the direct ion. Okay, so it told us that we have Fe2 plus in acidic medium. So that Fe2 plus is from the ion itself. So when we find the mole of this, then we can find the mass of ion. So mole ratio between the ion or ion 2 plus and MnO4 minus is what? From the equation, it is what? 5 is to 1. 5 over 1. What that means is that the mole of ion or Fe2 plus is going to be 5 times the mole of MnO4 minus. Okay, so 5 times this value, 0.727 times 10 exponent minus 4, will give us what value? So when we multiply that, we're going to have 3.364 times 10 exponents minus 3 moles. So that is the mole of iron. That is the mole of iron that we have. Okay. Now, the mole of Fe2 plus in the solution, to put it like that. Okay. So now that we know the mole, we are also given the molar mass. Okay. Over here, we've been told that the molar mass of Fe is 56. And, and so to find the mass of iron, all we have to do is to multiply the mole by the molar mass. Okay. Now the mole is 3.364 times 10 exponent minus 3. And the molar mass is what? 56. So when we punch that in the calculator, we're going to have a mass of 0.188 grams. 0.188 grams. So how do we find the percentage of iron? So let's just say percentage by mass, or percentage mass of Fe in ore. And this will be the mass of Fe over the mass of the ore times 100. So the mass of Fe, which we found here, is 0.188 grams divided by the mass of the ore, which is 0.350 grams, and I will multiply this by 100. Okay. And so what is the percentage? If you punch that, we are going to have 53.714%. Okay, so that's how you solve a question like this. Now, this is a likely question or a technical question that they can bring in your examination. So this is how to go about it. Now, the last question says, state the color change in the course of the reaction in II. So in the course of this reaction, remember it's a titration reaction. So now if we have a solution of iron 2, it usually has a green color, a pale green color. So initially you are going to have a green color, which at the end points will give you a pink color. Okay, so this is how you'll be able to determine that the reaction has come to an end. Okay, that will be the end point of the reaction. Now, I hope this video helps you in preparing for your exam, and all the best in your examination.